Welcome. Today we're going to factor polynomials. We are on 3.8 and we will do these problems from the homework. So we've learned many different methods of factoring. Before we jump into our first problem, let's just refresh our memory with a few of them. So some of our factoring methods include, first we always check if we can pull out a greatest common factor. We also know how to do difference of squares. We also know how to do magic X, factor by grouping, and a whole bunch more. So today we're going to see which ones work for these problems. Now they're not telling us what to try, so we have to kind of look at it and discriminate between the methods. So in problem number 1a, we always want to check GCF first, no matter what problem we're doing. Is there anything that we can pull out from every single term? Well, in 1a, notice that every term has an x. So even though I can't pull out a number, I can actually factor out an x first before I even begin. So if I divide every term by x, I'm left with x squared minus 12x plus 36. And now we can see, we have to look in here. Can we factor this further? Since it's a trinomial, we should probably try factoring it using magic X. So I need two numbers that multiply to 36 and add up to negative 12. The numbers are negative 6 and negative 6. So I can indeed factor this further because I just found some numbers that work. This can be rewritten as x minus 6 times x minus 6. And now I've factored the polynomial fully. That's our answer. Now, could you write it like this? X times x minus 6 squared? You totally could, because this is x minus 6 times itself, so you can also express it this way, but they're equivalent. So both of these are the correct answer. All right, let's do the next problem. Problem 1c. Okay, so we got to check, as always, is there anything that we can factor out? Can we take out a greatest common factor first? So number-wise, there's no coefficient I can factor out, and then they don't all have an a, because I have a constant term at the end with no a. So I can't take out a variable or a number. So GCF is not going to help us here. Next, notice that there's 4 terms. When there's 4 terms, we can try factoring by grouping. We'll try it and see if it works. So factoring by grouping works as like this. Underline your first 2 terms. Underline your second 2 terms. Now observe your first binomial, okay? This one right here. What can we factor out of both a cubed and 2a squared? I can take out an a squared, and then a squared times what gives me a cubed? That would be a. A squared times what will give me plus 2a squared? That would be plus 2. And I have basically done GCF on my first set of terms. Okay, now we're going to focus on this pair right here. Okay. So what can I factor out of both? Well, notice that they both have a negative in front. So I'm going to pull out a negative 1. And I'll be left with, if I'm pulling out a negative, that means that all my signs flip. So I'll be left with a plus 2. Look how well that worked out. This piece and this piece are the exact same. That means that factoring by grouping will work. And if I factor out the common guy, that's a plus 2, he gets his own. Okay, I've pulled him out. The common guy gets his own parentheses. And then what's left over gets its own parentheses. So that would be a squared minus 1. So the question is, have we factored fully? We just performed factoring by grouping, but can we factor it even more? And the answer is yes. Okay, look at that guy right there. I can factor that using the difference of squares. So recall, we'll take the root of the first term, we'll take the root of the second term, which is 1, and then we'll flip-flop our signs, a plus 1, a minus 1. And so our fully factored expression for h of a is like this. That's our final answer. Okay, let's try our last problem. Oh, I forgot to write it down. Okay, problem 2b says p of b equals 4b cubed plus 11b squared minus 19b plus 4. Okay, so example 2 says you'll need to use rational root theorem. Rational root theorem works like this. If I had already been given a factor, then I can, like let's say they had said, hey, b minus 3 is a factor. Let's just hypothetically pretend that's what it said. If that was true, then I would go ahead and try plugging in my root of 3 and doing synthetic division from there. However, they're not even giving me a starting point. At least if they gave me one of the factors, I would know where to begin. But since they didn't even give me a starting point, that's where rational roots theorem helps out a whole bunch. So let's take quick notes on rational roots theorem and what it does. So our rational roots theorem, it basically gives us a list of possible roots. This is helpful because it'll get us started on our synthetic division. It'll tell us which numbers to start plugging in. And so your notes from class should look something like this. P over Q, where P represents all the factors of the constant term. And Q represents all the factors of the leading coefficient, or the leading number. So just as a quick example, if I was given 3x to the 5 minus 4x cubed plus 2x minus 10. Well, my constant term would be 10. My leading coefficient would be 3. And so then my rational roots would be the combination of all the numerators and denominators for the factors of 10. So that's going to be plus and minus. What are the numbers that go evenly into 10? That's what factors means. Numbers that go evenly into, or that multiply evenly into 10. Well, that would be like 1, 2, 5, and 10. And then in the denominator, I need all the numbers that go evenly into 3, which would just be 1 and 3. So once I've listed them out, now I need to actually try all these combinations. 1 over 1, 2 over 1, 5 over 1, and so on, and list them out. So first, I'm going to use this denominator and try every coefficient with that denominator. So 1 over 1 is just 1. 2 over 1 is just 2. 5 over 1 is 5. And 10 over 1 is just 10. Don't forget we're trying the positive and negative versions. We're not done. We also have a second denominator to try everything with, and that's 3. So we've also got 1 over 3, which does not simplify. 2 over 3, 5 over 3, and 10 over 3. So you kind of see the pattern there. 1 over 3, 2 over 3, 5 over 3, and 10 over 3. And I would basically proceed with these in my synthetic division. So in this case, let's go back to our problem that we're given, which is, I'm going to rewrite it, 4b cubed plus 11b squared minus 19b plus 4. So since I'm not given a starting point, I need to use my rational roots theorem to come up with the possible roots, my possible starting values. Okay, so possible roots would be plus or minus, and I'm going to list all the factors, all the numbers that go evenly into 4, And all the numbers in the denominator, I'm going to put all the numbers that also go evenly into 4. So in the numerator, 1, 2, and 4, that's for this guy. And in my denominator, all the factors of 4 are also 1, 2, and 4. Now, I got to actually try all the combinations, just like we showed in the notes. So let's try it. Let's first start using 1 as our denominator. Okay. So that means we have plus or minus 1 over 1 is 1, 2 over 1 is 2, and 4 over 1 is 4. Next, we'll try 2 as our denominator. Well, 1 over 2 is 1/2. 2 over 2 actually simplifies to 1, but notice I already have 1, so I don't even need to write that one down. And then 4 over 2, hey, that also simplifies. That's just 2. I already have that one written down. So again, you don't need to write any repeats. Actually, here's what I'll do. I'll write the repeats, but then I'll cross them out. So we also had 2 over 2 and 4 over 2. Now this became 1, which I already have. So I'll cross that out. And this became 2, which I already have. So I'll cross that one out. Okay, let's try our last denominator. So I have, let's start with 1 over 4. And then I have 2 over 4. And then I have 4 over 4. Well, 1 over 4 doesn't simplify. 2 over 4 becomes 1/2, which I already have, so I'm not going to write it. I'm going to cross it out. And then 4 over 4, that's really just 1, which I also have already, so you can cross it out. So my final list is plus or minus 1, 2, 4, 1/2, and 1/4. All right, so we're going to start by trying positive 1 and see if that's a root. Because if it is a root, if A is a root, this is some important notes, then x minus A, basically flip the sign, is a factor. And once we have one factor, it's easy to find all the others. Please take that down. Okay, so let's see if 1 is a root. If it is, then I should get a remainder of 0. Okay, so let's try 1. 4, 11, negative 19, and 4. Bring down the 4. 15. Minus 19 plus 15 is negative 4. Negative 4 times 1 is negative 4. Hey, look at that. 4 minus 4 is 0. So since our remainder is 0, that's a good thing. That means 1 is one of our roots, meaning that x minus 1 is one of our factors. So that means x minus 1 times 4x squared, I'm rewriting this as the answer, 4x squared plus 15x minus 4. This times this will get me back to my big original expression, P of B. And I didn't mean to write x's actually, I should have written b's. So that's b minus 1 for b squared plus 15b minus 4. There we go. So now let's look at what we have. Let's see if we can factor this anymore. Let's try magic x. I need two numbers that multiply to negative 16 and add up to 15. Those would be 16 and negative 1. Now I can't use my shortcut because there's a number out in front. So I've got to rewrite this. Let's just work on factoring this right now. So we've got to split our middle term. Or minus 4. Okay, we'll use factor by grouping. We can take out a 4b, and I'm left with 4b. Oops, I can take out a 4b, and I'm left with b plus 4. And over here, I can factor out a negative 1, and I'm left with b plus 4. So for our final answer, we have 4b minus 1 times b plus 4. And that's just this piece. So my fully factored expression for p of b is b minus 1. I'm just bringing it down. times 4b minus 1 times b plus 4. This would be our final answer. Okay, I hope that was useful. Good luck on the homework. I'll see you next time.